Hey guys, I just wanted to kind of get in touch with you all and kind of try to keep our momentum on the unit that we were working on before the last day of school, which I wasn't even able to be at, so I'm sorry I missed everybody. But I wanted to go ahead and give you access to this last section of notes so that we can kind of wrap up this unit as soon as we get back, which hopefully we will. We'll just be optimistic that way. So, our last section of notes, so for Unit 8, Section 4, we're going to talk about a few exceptions to the octet rule, and then we're going to talk specifically about some molecular shapes. And you guys had a little bit of an intro to that when we did that PhET simulation activity online that Monday that I was last there. So first, we're going to talk about some exceptions to the octet rule. It's just like I always say, there's an exception to every rule, and the octet is no different. So there are some molecules that do not obey it. The first type of molecule that does not obey the octet rule is a molecule that has an odd number of valence electrons, and I've provided you with an example of that. Nitrogen dioxide has 5 valence electrons from nitrogen, and there are 12 from oxygen because there are 2 of them, so 6 times 2. And so it cannot form an exact number of electron pairs. So in other words, you have this single one right out here that is all by itself. And so that leads to an odd number of valence electrons, and if you have an odd number, you can't obey the octet rule, but this molecule does exist. Our second exception to the octet rule is something called a suboctet. And there are a few compounds that are able to be stable without having 8 valence electrons. They will have less, usually 6, and that exception is called a suboctet. Most of the ones that you'll come in contact with are involved with boron right here, which is a metalloid, so it tends to do covalent bonding. And so an example of a suboctet would be this molecule right here, boron trihydride. And as you can see, if I count up these valence electrons, 2, 4, 6, because each one of those lines represents a bond between 2 electrons, dot, dot, and then a line. So I have a total of 6 electrons around the boron, which is not an octet, but this molecule is stable and does exist, so this is an exception. Our third and final exception to the octet rule are these molecules that have an expanded octet, and the elements that are in period 3 or higher, or 13 or higher if you want, have a d orbital and can form more than 4 covalent bonds. So in other words, they can have a greater number than I said was originally possible when we first learned, because we saw that carbon that has 4 valence electrons had the most opportunities for bonding. However, there are these select few elements that have this ability to do an expanded octet, and you can see phosphorus doing it right here. This is phosphorus pentachloride because there are 5 chlorines here, and if I count the electrons around phosphorus, you'll see that there are 2, 4, 6, 8, 10. So greater than 8, so an expanded octet, more than 8 valence electrons. So all in all, there are 3 exceptions to the octet rule: the ones that have an odd number of valence electrons, the suboctet, the ones that can be stable with less than 8, and then the expanded octet, the ones that can have more than 8 valence electrons. So above 8, usually up to 12. So now that we've covered the exceptions to the octet rule, we're going to go over the molecular shapes and what I expect you to know as far as molecular shapes. And shapes are important because they determine many of the molecule's physical and chemical properties, and the molecular geometry or the shape of a molecule can be determined using this specific model. It's called the VSEPR model, And the VSEPR stands for valence shell electron pair repulsion. And so it is an instruction manual to show you how to arrange your electrons and bonds around the central atom to show the true shape of the molecule that you're building. And the main points of VSEPR are listed here. It says that electron pairs repel each other. Of course we know they repel each other because electrons are negative, and so that like charge makes them not want to be around each other. Opposites attract, but since electrons are all negative, they do not like to be around each other, so they will repel. So they repel each other, and so what this causes is for the molecules to be in fixed positions, and so any unshared electron pairs also determine the shape of a molecule because they are going to repel all of the bonded electrons as well. And so what you want to do when you are building a molecular shape is that you want all your electron pairs to be located as far apart as they can be. And so anytime I've drawn one, I've tried to be consistent in doing that, and I've told you that I do that because it would help you down the road, so this is the reason. VSEPR. So now, getting to the actual shapes, what you need to know about them, and the ones that you'll need to be able to determine as far as the test goes. There are 5 molecular shapes that I want you to know, and the things that I want you to know about them are their names, the bond angle created, which molecules are going to take that shape, so you need to be able to determine the shape of a molecule and be able to name it and write the bond angle for it, and draw it correctly. And you always want to draw it with the electrons as far apart as possible, which I'm going to try to show you. So I'm going to use the program that we were using on that assignment that I gave you that last day I was there. Our first shape that I want you to know is linear, and this right here is an example of a linear molecule. So you can see that the name is obvious. Everything is in a line. And if you try to get the bond angle using this program, it won't give it to you. And a question about that is on that actual assignment that we were working on with this program, so I'm going to let you guys try to decide the answer on that. But I'm going to write the bond angle here. We're going to go ahead and draw one of these like they normally do. The bond angle on a linear molecule is 180 degrees. And if I were you in your notes next to the linear part that you just wrote, I would go ahead and draw this, the best of your abilities, include the bond angle on it. This is just to give you an example of another molecule that looks different from the one I just showed you, but is still linear, is carbon dioxide. And so the one that I have on the screen right now is carbon dioxide, because when you actually put carbon dioxide together, you'll have the carbon in the middle, double bonded to oxygens here on the outside. And if you see, when you build that in this program, it actually comes out to be a linear shape, and it confirms it right down here at the bottom. So no matter how I try to move those electrons closer, you notice what happens. They'll always try to be as far away from each other as possible, just like VSEPR tells us they should be. So anytime you write something like carbon dioxide that would be linear, the reason that it's linear is because these electrons want to be as far away from the others as possible. The ones that are in the double bond, they're in a double bond. There's nowhere for them to go. But if I try to get these bonded ones next to these bonded ones, it's not happening. Okay? So that's what you have to remember when you're trying to determine your shapes. The second shape that I want you to be familiar with is called trigonal planar. This is a trigonal planar shape. You can see that the trigonal part comes from the fact that there are basically 3 spokes right here. And then the planar part means that it is flat. I could lay it flat on a tabletop, so you can kind of see that. So it kind of forms just basically a little triangle. And once again, I'm trying to move those bonds closer to each other, but no matter what, they stay at this angle because all of these electrons want to be as far away from each other as possible. So if I click Show Bond Angle, it will show me that in a trigonal planar shape, the bond angle is 120 degrees. So you need to make sure that you draw that in your notes and show that bond angle right there. This program is actually really awesome for practicing your molecular shapes. To show you another example of a trigonal planar, just so you know that it's not just single bonds where this could show up, if I do a double bond and then two singles, I still get trigonal planar as the result, and my bond angle is still 120 degrees. So this is a trigonal planar molecule as well. Okay. So back to our main screen here, if I were taking notes, this is the type of thing that I would be doing. I would have my molecular shape, the name listed, and then I would have a little drawing here with the bond angle included, and then maybe an example molecule. So CO2 would be an example of linear, and BH3 would be an example of trigonal planar. Our next shape is going to be tetrahedral. And this is what a tetrahedral molecule actually looks like. You can see the tetra means 4, so you have the 4 attachments. So they're fairly easy to identify, and as I move it around, you can see that the electrons still want to get as far apart as they can as possible, following the VSEPR model. If you were to see this in real life, what it actually looks like is, if I were to set this on the table, you would see these 3 things would cause it to kind of stand up on the table, and then this would be poking straight up out of the top. So it kind of looks like something with 3 legs and then kind of a head at the top. And then if I click show bond angles, you'll see that they are 109.5. And for an example of something that is tetrahedral, we can always switch over here to the real molecules section. And then if I look through here, something that would be tetrahedral would be CH4. So you can see that exact tetrahedral shape right there. And if I show bond angles, you'll see that it's 109.5, which confirms the tetrahedral. But if I wanted to be even more sure, I could click the molecule geometry and it would show me. So there's your example of a tetrahedral molecule, your bond angles, and a real life example. Our fourth shape that I want you to be aware of is trigonal pyramidal. This is where they get a little bit more complicated because they're going to include some lone pairs. So something that is trigonal pyramidal is going to have at least 3 attachments, and then what causes the pyramidal instead of planar, because this right here is trigonal planar like we saw earlier, so what causes something to become trigonal pyramidal is the addition of one of these. And you can see how that changed my bond angles quite a bit. So what these actually look like if you build a model is just something that can stand on 3 legs because you have an imaginary lone pair up at the top there. But this isn't the real bond angle. Where we have to get the real bond angle is to switch over here, which hopefully you would have seen in that last assignment that we did, though I know it's been a while. This right here is an example of a trigonal pyramidal molecule, NH3. If you do NH3, you have the 3 bonds to the hydrogens here, here, and here, and then you have that remaining lone pair, which is those right there. So in a drawing, this molecule would look like this, but that translates out to, in real life, looking like this. So these 2 dots right here are those 2 dots right there. So you can kind of see what they would really be like. And that is the true bond angle of a trigonal pyramidal molecule, 107.8. The last shape that I want you to be familiar with is the bent shape, which I've been drawing it for a long time because I've been showing you water for quite some time, but I'll go ahead and show it to you again. So bent molecules have 2 attachments, so I'm going to use those as an example. And if I just do that, this is a linear molecule. So what changes a linear molecule into a bent one is if we have a couple of lone pairs. So this is what causes it to be bent. So if I turn it just right, you can see this bent shape occurring here. And if I move over to real molecules and show you something that really has this shape, H2O, now you can really see it. So there's our two lone pairs at the top, and then our two attachments to our oxygens. The bond angle on this is 104.5, which is kind of hard to see right now, but I'll try to get it. You can see it. There you go. 104.5 is your bond angle for a bent molecule, and an example of a bent molecule is water. So now I've shown you all of the molecular shapes that I expect you to know, and so the next time that you're drawing a molecule, you want to follow the VSEPR model and place your electrons as far apart as possible and determine which of these 5 shapes that molecule is going to take. So just to give you an example of what I'm really expecting you to do from this information, I've given you some example problems right here. And the first thing that you're going to want to do is just simply figure out the bonding and draw it. And once it's drawn, you need to figure out which of those shapes that we just looked at that this really matches, and then add your bond angles in. So I'm going to give you a break right here to try this on your own, and then I will give you the answers here in just a little bit after you've tried it. So your first molecule that hopefully you went ahead and tried was boron trifluoride. Got to review your naming as well. So if you're doing that, if you look at boron first, because it's the least electronegative, it has 3 valence electrons, so it's going to look like this. And then you have fluorine, which is a halogen, which can only make single bonds, so that makes this kind of simple. Just put your fluorines around it like this. So that there's your 7 valence electrons, and then if you look, there's a bond, there's a bond, there's a bond, which translates to being looking like this with our dots. And traditionally, right here is where we would stop. However, since we just learned some new information, we can incorporate that information. So once you get to this point, according to the VSEPR model that we just went over, those electrons want to be as far apart as possible. So you could redraw that. I'm going to use a different color. You would redraw that with your new information to make them as far apart as possible. So your final drawing should look actually like what's in red here. And if you're looking back at those shapes we just drew, you'll see 3 attachments, but no lone pairs, which means that this would be trigonal planar. Okay, so that makes this bond angle right here 120 degrees. So that's the answer to number 1, this right here. Trigonal planar molecule, which means that your bond angle is 120 degrees. And if you ever want to confirm your answer while you're at home, use this program. It's so awesome. If you pretend that this purple atom right here is your central molecule of whatever you're drawing, so for instance, this would be boron right here, and you're like, you know what, I think it was 3 single bonds with nothing left over, because boron only has 3 valence electrons, so it has to look like this. This already tells you, hey, it's trigonal planar, 120 degrees. So you can confirm your answer right there. Second molecule was this right here. So you'll have your oxygen that has 6 valence electrons. Then you'll have your chlorines with their 7. So there's one bond and there's another. So if I rework this, it's going to end up looking like and then I have my 2 lone pairs. I can see them right there and right there. The only molecular shape that had 2 lone pairs. And then if I spread out the electrons as far apart as possible like I did, that would be a bent shape, which means that this bond angle right here is 104.5 degrees. So then CF4, hopefully your drawing would come out like this. There are 4 attachments. The only shape that we talked about that has 4 attachments was the tetrahedral shape, which means that this bond angle right here would be 109.5 degrees. And this drawing is correct because I've put all of these bonds as far away as possible. And then carbon dioxide we've already talked about quite a bit, and I've drawn it a few times. And we talked about in this actual video that carbon dioxide is linear, and because this bond wants to be as far away as possible from this bond, so they just go on opposite sides of the atom like that, which means that this is a linear molecule, and so your bond angle is going to be 180 degrees. So you guys, that pretty much takes care of the last section of notes for this unit. So what I'm going to be doing is kind of putting out some review materials every couple of days or so, and as we progress towards hopefully going back to school, I'm going to put a study guide out probably at the beginning of next week, and then very soon after we return we're going to be having a test. So it is my strong recommendation that you get these notes taken down, you take advantage of the practice materials that I'm going to be providing, and you get that study guide done and you're ready to go when we get back to school, because there's going to be a test very soon so that we can move along. And I know that you have that assignment that we worked on Monday, and I said you could stop before the post-lab questions. Well, now that you have this information from this set of notes, you can finish that assignment, and we're going to turn that in when you return. So get those post-lab questions done and be able to turn in that assignment when we come back, okay? I really look forward to seeing you guys. It's really hard for me to sit here at home, so please stay at home, stay healthy, so we can get back to school and get back to seeing everybody. So I hope to see you all soon.